Hello, everybody.
Yeah.
Hello.
Hello. Couple of comments. Homework 10 is due on Wednesday. Homework 11 similarly. April 26th, it is a Monday. And a small change. Homework 12 was April 30th and Friday. That remains pretty much the same. The change is that I made this optional. Which means that if you do not attempt on it, you don't lose anything. But if you have missed any other homework, if you attempt on this, then the average scoring reduces. So if you have lost some points in your earlier homework, so then you want to do this. Not that you will get back the whole thing from the back, but after you average it out, it might improve your score. So, and since it's the last week, I thought I will make that optional. And during the last week, I also complete the D2L and I decide on whether to drop some homeworks or quizzes. So keep watch on that, but it will be for the whole class. It won't be on a personal basis. So that's about the homeworks and final exam. Is May 6th. Thursday. I should also go over the quiz from 14. So quiz talked about what if you have a sphere rolling on a surface. So that's a surface and you have a sphere that is rolling along. If it is perfectly rolling, notice that the velocity of the center of mass, so that's moving, so that's your velocity v, and the rotational motion, you have its angular velocity decided by omega, and if the radius is, let's say, r. So these quantities are related if you're perfectly rolling. So that's one thing. And the question asked, what is the torque exerted by the normal force? So for that, first of all, we need to know what is the direction of the normal force and where does it apply to. Also in this problem, it doesn't play too important a role, but it's important to know that the gravitational force acts on the center of mass. Notice the tail end of the vector. So that's your, maybe I should erase this and draw this again so that there is no clutter. All the information stays the same. So that's your center of mass. Gravitational force acts at the center of mass. That's your mg. When it comes to the normal force, it is exerted by the surface, and that's acting at the interface of the two objects. That's your normal force. Notice this is acting at the right at the bottom of the sphere. Either way, and this is, I've shifted it a little so that I can show this. This is actually along the same line. In fact, it goes through the center of mass. And then if you do r cross n about the center of mass, that's your torque due to the normal force, where r is the distance from the center of mass to the point where it is acting. So if I were to draw that again here. So that's your R. That's not a force. And these two are along the straight line. If I were to draw this again separately here. So that's your center of mass. That's your position where the normal force is acting. That's the bottom of the sphere. And the normal force, if I were to move this away, like remember that vectors can be moved parallel to itself. So that's R cross N. And you notice that the angle between them is 180 degrees. So the magnitude of torque is R times the normal force times the sine of 180 degrees, which is equal to 0. So that's equal to 0. So that's the exercise that was given for the quiz. Today, we want to talk about rotational inertia. And by inertia, we mean mass. Like what is the quantity that acts like mass when you're talking about rotations? So go back. What is the summary here? What are we talking about? We are talking about rotational motion in the context of after removing the translational motion. So there is a time involved. In translation motion, we used to talk about linear velocity or translational velocity. Here we talk about translational displacement. Here we talk about rotational displacement. So this is rotational displacement, or we call it angular displacement, right? I think same idea, but the technical word is angular displacement. We defined angular velocity as the derivative of the angular displacement. Which is the same idea as we have velocity here, which is defined as the derivative of translational displacement. Angular acceleration is second derivative of the angular displacement, or the first derivative of angular velocity. Angular acceleration. And here we had the similar idea was acceleration. Now from this point on, we had two more concepts come in, and that was mass and force. So there is mass in here, there is force here, and most importantly, we said that for mass times acceleration was force. And let me write that equation slightly differently. Let me write acceleration as force per or force over mass. And it should be read in the following manner or interpreted in the following manner. Acceleration is what describes motion for us of the mass m. And we are talking about what helps motion. That's the force. If you exert more force, there is more acceleration. And colloquially, we say it contributes to the motion. What resists motion is the mass. Like if you have more mass, it is harder for things to move. In the same spirit, we want to talk about what is alpha. We have already talked about what helps angular motion or rotational motion, and that we said is torque. So that was torque here. That was what was introduced last time, and that's R cross F. It's not just the force that matters, it is the force times where it is applied. Like there is a axis that determines the angular motion. Everything is happening with respect to an axis when it comes to rotational motion. And this R decides, or this R is the place at the point with respect to the axis where this force is acting. Right? Where you exert the force is important. So it depends on torque then. So the angular acceleration depends on the torque. And now we want to ask what resists angular motion. We will call this rotational inertia, I here, and we want to find out what does this depend on. Here this was R cross F, this is a scalar as it sits here. What is it that resists rotational motion? Since we already know the idea of torque and we know alpha, remember dimensional analysis will help us a lot here. We can at least know what are the dimensions of momentum inertia. That will tell us what does it depend on. So let's look at the dimensions. So I, moment of inertia, is equal to, no, I meant, if we wrote alpha is equal to torque over I. So if you're interested in the dimensions of I, we would say this is the dimension of torque, right? It's a vector, but when it comes to dimensions, we only have to worry about the magnitude over magnitude of the angular acceleration. Torque is force times distance. So this is R cross. The cross doesn't contribute anything. It is sine theta that comes in. Remember, it is magnitude of R times magnitude of F times sine theta. Sine theta does not have dimensions. It only gives you a number. And that's your dimension of alpha. So that's equal to dimension of R is length. Dimension of force is mass times acceleration. Acceleration is length over time squared. So that's LT minus 2 divided by alpha, which is angular displacement over time square. Like there are two times there since it's a second derivative. Angular displacement is angle that doesn't have any dimensions. So it is simply T minus 2. And we notice that these two cancel out. So it is ml squared. And there is no time dependence in it. That tells that it surely depends on mass. So what equation is telling us is that moment of inertia depends, is proportional to mass, and it is proportional to length square or distance square, and whatever that distance is. It's clear here that since we are talking about angular motion, it must be the distance from the axis of rotation. So if we have a single point mass, it should be mr squared. So let's define now. So we define at this stage. Rotational inertia, I, will be equal, for a single point mass, it will be m times r squared. What is r? R here is the distance of mass m from the axis. Remember, whenever we have rotation, we have to have an axis associated with that rotation, and distance r is the distance from the axis. And whenever we talk about a distance from a line, we are talking about a perpendicular distance. There are lots of points on the line, so we are talking about the distance of the closest point on the line. So if the rotation is happening in this plane and the axis is coming out of the board, so it will be rotational inertia would be, this is your axis. So it's
The
coming
camera
out.
needs to be moved.
Oh, thank you. Thank you, thank you. So if we are talking about a single point mass rotating about an axis, so that's your axis that is coming out of the board. Remember that this is coming out of the board and that's not visible again. That's coming out of the board and that's going into the board, right? So that's the notation here. Cross means going into the board. Point inside a circle means coming out of the board. And there is a mass M. So let's say that's your point mass. That's your mass M. And that's moving in a circular orbit about this axis. This distance is R. And we are saying that how far it is decides how much is the moment of inertia or how much is the resistance to motion will be simply M R squared. So that's simple. The only catch now is that what if there are more masses? So there is one mass here, the second mass here. So there are all distances here, and you could distribute this about the axis all over around its axis. And we want to talk about what its rotational inertia is, or how does it resist motion. Imagine you're holding something non-uniform and you're trying to rotate it. Is it convenient to rotate about one point versus another point? So let's look at that. So let's do it. Example. So let's have a single rod, and let's have that a mass M2 here, and at the other end we have mass M1. So that's 1, that's 2, that's your M1. Let's say M1 is 10 kgs and M2 is 2 kgs, just to give some numbers. It's 10 kg and M2 is 20 kg. Let's say the length L between them is 1 meter. So that's length L. Let's ask. So case 1, let's say. Question 1 is what is the moment of inertia? So what is the moment of inertia about an axis going through M1, passing through M1, and I should also specify that it is perpendicular to L, right? And perpendicular to L, right? There's a line L, so it is perpendicular to that. That means it is coming out of the board. So first we will do what will happen if you had an axis here and it is rotating about that point, and you will move the axis here and then again do the rotation and see which one is easier to move, right? Imagine you have a heavy object on two ends. Which one will it be? Which one will be easier to rotate about? Remember, it depends on, it is proportional to the length. So it is not just the masses that matter. It also depends on where the masses are. So first we have I. There are two masses, so we will do M1 times R1 square plus M2 times R2 square. So there's nothing, no division, so I can just write it here. M1 R1 square plus M2 2 square. The axis is right here. So let me, so this is the axis itself. So that's your axis. So how far is the axis from mass m1? That's 0. So that's m1 times 0 square plus m2, which is 20 kgs, times 1 square. So that's 20. What's the unit? It's kg meter square. That doesn't help much with intuition because we just have one number at this point. So we should compare it with what happens if you had the axis on the other side of the rod. And let's do case 2. So case 2 is the same question, but about M2. We have I this time, same idea, M1 R1 square, M2 R2 square, but the distances now are relative to the right hand side. So it is M1 times 1.0 square plus M2 times 0 square, which is 10 kg per meter square. Rotational inertia or rotational mass is larger when you're on the larger when you're in case 1 where your axis is on the left side. So larger means it will be harder to move things when you're rotating it about this axis. Notice that this is more massive. But all this, I have taken the extreme scenario where the center of or the axis is on the either end of the line connecting masses M1 and M2, but that doesn't have to be the case. I can have an axis somewhere here, 20 centimeters down the line. I can talk about what is the moment of inertia about that. And you could be rotating this rod about this point, right? And you can ask again how easy it is to rotate it. And that's what we are trying to quantify with the idea of moment of inertia. So that's good. In your homework, there is a problem discussing. So we have a system like this. So it doesn't have to be, so let's say that I think you have only one rod in there. So, but in principle, you could talk about all these masses. These lines here are simply abstract lines there, or you can say massless rods there, and you could have M1, M2, M3, M4, M5, and M6. So that's just a way of distributing the masses. And now we ask, where is the axis? So a simple situation where you can keep the axis is here, right? So that's your axis. So that's your axis. And now imagine you're rotating this whole thing in the plane of the board. And what matters is the distance. So you should be able to calculate this distance, this distance, and also this distance, right? If you're given this vertical and horizontal distance, you can calculate it. So this will be R5, right? So this will be R4, and that's R2, that's R3, and so on. And do the same idea of M1 times R1 square plus M2 times R2 square and so on. So the main idea is that it depends on the axis, and you should be able to clarify that. Here, let's do some examples where the mass is not uniformly distributed, and that involves integration. So the discrete scenario, which is significantly simpler, will be dealt in the homework. And here we want to talk about what if the mass is continuously distributed. So that's so moment of inertia. So let me call it I for continuous distributions. We have I is equal to summation over I times mi times ri square, right? That's what we did, m1 r1 square plus m2 r2 square. If there are n pieces, this will go from 1 to n. This is what happens if you have discrete masses, mass distributions, if you want. If you have a continuous mass distribution, summation immediately generalizes to an integral, and you integrate over a distance. And if we are doing in one dimension, this will be just x squared. If it is two dimensional, it's the distance r square x square plus y square plus z square if it is in three dimensions. And usually there is a limit. So what is your dm? So let's do some example to clarify what that dm is. So let's do the simplest example of a one-dimensional object. So we have just a rod. And the moment we say a rod, and if we are talking about moment of inertia, we have to specify where the axis is. So axis is on one end. It is on one end of the rod. So this is your axis. That's coming out of the board. So that's your axis. And the line itself is, the rod is simply a straight line, infinitely thin rod, let's say, and it has a length L. Let's say this is length L. Let's also say it is uniform rod. So we say that this is uniform rod. And what does it mean to say it is a uniform rod? That means mass per unit length. So when we say that is a rod, there must be a mass associated with it, but mass per unit length, the total mass over total length is a constant. Okay. It's uniform means also means that I can pick any small stretch of this rod, calculate the mass of that tiny piece divided by the length of that will remain the same lambda, which means that I can also make it really tiny element here. So let's say this is a tiny element of the rod there. So that's dm. And its length is dx. Right? The tiny element has an infinitesimal mass m and infinitesimal length dx. And it will be the same. So dm over dx will remain the same. So that's our idea of uniform rod. Mass per unit length, since it is any stretch, I will say this is the total mass over total length. So that's your total mass over total length. So we have a relation that is a uniform mass density, if you want, linear mass density, mass per unit length, which is also infinitesimal statement in the sense dm over dx is lambda. We would like to calculate the moment of inertia, which is start from the axis and you add up all the tiny elements. So there is a tiny element dm somewhere here. How far is it? It's a distance x from it. So that's your x squared. This tiny element, how far is it? That's x squared. And now you want to add up all such elements. So there is a tiny element here, here, here. You have to add up all this. So where are you adding it from? From the axis and all the way to L. But we are adding over m, so it is not really easy to specify. There is no order in this mass distribution, right? So we want to convert this dm into dx so that we can put some limits, so that we can put a lower limit and an upper limit. So convert dm to dx. So that will be equal to dm is equal to, forget the lambda here because we would like to write the answer in terms of mass and length. So it is m over L times dx. So that's equal to dm is mass per unit length. Oh, by the way, it doesn't matter whether I write dm here or on the other side. Often in mathematics, it is more common to write the dm factor at the end of the integral, but it doesn't matter. Especially when there are more than one integrals, it is good to associate the differential element with the integral sign itself. But that's just a matter of notation, but feel free to write it on the right side if you prefer it that way. So in principle, it can be anywhere, right? So that's your x squared. That's your moment of inertia. But now, since we are integrating over x, we have a very nice or unique way of saying where the integral begins and where it ends. So it's a definite integral in that sense. And here we say that it starts from x equal to 0 and you go all the way to L. So you start from a point very close to the axis and you go all the way to the length L. That's an easy integral. Mass and L are constants that comes out of the integral. This is simply dx x squared. So this is m over L. Dx x squared is x cubed over 3. So that's x cubed over 3. And it'll go from 0 to L. That's L cubed over 3. One of the L cancels out. So our moment of inertia is 1 by 3 mL squared. Notice it would have been very difficult to get that factor of 1 by 3 if you do not do this integration. It is pretty much like asking if I were to find out why do we have the volume of a sphere to be 4 pi r cubed. Only way you can get this 4 by 3 factor there, or 4 pi by 3 factor, is by integration and doing the summation over all different points. There are various ways of doing it, but unless you do that mathematical exercise, you cannot guess on that 4 pi by 3. On the other hand, this cube you could have guessed using the dimensional analysis feature. The dimension of space actually tells you what that 3 is. But 4 pi by 3 has to come from a detailed calculation. And similarly, this 1 by 3 has to come from a detailed calculation. There is no other way of guessing it. So if you're not familiar with calculus, we will not be able to get this factor of 1 by 3. So what we have is that if you have a moment, have a rod and you're rotating about one end of the rod, then its moment of inertia or its resistance to rotational motion depends on the mass m, depends on the square of the length L, and it depends on a factor 1 by 3, which is purely geometry, purely coming from the geometry of the object. Let's now move this axis to the center of the rod and see how things change, right? One would think that, or we pointed out that it actually depends on the position of the axis. So let's see how it changes if you were to move it to the center of the rod. So the same exercise of a rod, but this time the axis is about the center. So the diagram is, that's your axis. That's your axis, and this will be now length L over 2. This will be length L over 2. Right? Since it is at the center, that's where you are. Most of the understanding remains the same. It's a uniform rod, so mass over length, which is the lambda, which is also equal to an infinitesimal statement. You pick any small length along the rod, and it should have the same density. So that gives us this. And if you were to now integrate this quantity, we have I is equal to dm. And so this is your small element here, which is dx, which is having a mass dm associated with it. So dm, that's your dm, and how far is it? That's your x. And so that's your length x. And what we mean here is that we are summing over all masses. So you have the dm, 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 you have to add up every small element there. But there is no order when we talk in terms of masses, so we want to convert it into dx. So dm is mass per unit length times dx, and that is an x squared. But this time, in this limits, everything is the same as earlier, but now the limits are minus L over 2 to plus L over 2. And that will change the answer. Right, so notice what happens. So this is the same idea as earlier. This is mass over length comes out of the integral. The integral of x squared is x cubed. But now you don't go from 0 to L, you go from minus L over 2 to plus L over 2. And that gives us mass over length times L over 2 cube minus L over 2 cube. That's only difference. L cube is the, oh, that was an x cube over 3, right? I forgot. Sorry about that. So this is x cube over 3. Sorry for that confusion. So that's 1 over 3 then there. So let me put that common outside. So there's a 1 over 8 coming in here, 1 over 8 coming in there. But since this is a negative sign, this negative sign raised to 3 still remains negative. Negative plus negative is positive. So 1 over 8 plus 1 over 8 is 1 over 4. And there are and 4 into 3 is 12. So this is equal to 1 by 12 ml squared. So if it was on one end, so if it was on the end of the rod, the moment of inertia was 1/3 ml squared. And if it was on the center of the rod, it is 1/12 ml squared. Which one resists more? Whichever has larger moment of inertia will resist the motion more. So it will be harder to move the rod about the end if you rotate it about its end versus if you were to rotate it about its center. Right? Again, if you have practically tried this out, try to rotate a rod with respect to some point, you will notice that it is harder to rotate, significantly harder actually to rotate about its end. So those are slightly simpler examples. We will, in our examples that we will deal with, we will talk about rolling cylinders, rolling spheres, and we will also have the option of making the cylinder hollow inside. And we can also have the sphere hollow inside. So we should also find out what is the moment of inertia of cylinders and spheres. And of course, we have already done this for the rod. And we won't be able to do all the integrations here in the class, but I will give you the result. And as I said, this 1 by 12 and earlier 1 by 3 can be got only from doing this as an exercise in calculus or anything related to that. So there are various ways of doing it, but mostly you should be able to divide this large element into tiny, infinitely tiny elements. So let's I'll go about three-dimensional objects. So the examples, let's say three-dimensional objects. And we will mostly restrict our analysis to just spheres and cylinders, and that too out of that there can be two from each. Each of them can be hollow. So let's list them. So, and remember your axis is also important. So this is your object, and then we will say what is the axis. So first we will have a hollow cylinder. This will be a hollow cylinder. And immediately I have to say this axis, right? Hollow cylinder about its symmetry axis. The axis is a symmetry axis. By that I mean, so this is your cylinder. So that's your axis. By that I mean the symmetry axis. So a cylinder has an axis of symmetry. That's the point about which we can rotate. But it doesn't have to be rotated that way. Remember, you could rotate it about this line, right? Going perpendicular to that, like a rod, for example. If the cylinder was sufficiently thin, then the rod we talked about just now was the axis for that was perpendicular to the symmetry axis. But often when you're rolling a cylinder, it is this axis that comes around. And we will mostly talk about rolling. We are doing a very simple exercise here in the limited time we have. So that's hollow cylinder. So then we will talk about a solid cylinder. And I will talk about that, but to leave a line here, I want to introduce another geometry in there. So it's solid cylinder, again about the symmetry axis. So the only difference between the two is diagram looks exactly the same, but now this is solid in the sense that, so this is solid. The diagram tells that it is completely filled with mass. Instead here, it is about a ring. So that's your axis again. I should also specify that if you're rolling a ring, that comes out to be exactly the same as a hollow cylinder. And this could be a finite solid cylinder in the sense that the length of the cylinder could be finite. So ring and hollow cylinder pretty much behave the same way. So solid cylinder, hollow cylinder, and I'm writing it in a hierarchy here. So this will have the largest moment of inertia next. So that's why I left a space there. And here I want to talk about a hollow sphere. And what is the symmetry axis here? You will say about an axis passing through the diameter, passing through diameter. What's a diagram? You have a sphere and think of a axis that's passing through the diameter, pretty much like the way our Earth is moving about an axis that's passing through the North Pole and the South Pole. So that's your motion. So that's your axis. That's clear. And the difference here between a solid sphere and a hollow sphere will be all the mass is distributed on the surface of the sphere. Unlike Earth is a solid sphere. Imagine all the, like if you were to enter the Earth and it is completely empty. So that's the way to imagine that. And we also have a solid sphere. Again, through the diameter. Diagram looks very similar, but I will specify by saying that these are lines here and there is an axis according to the axis. So do the same thing, but this is now solid. By solid, I mean it is filled with mass all the way from radius 0 to radius r, let's say. All these are uniform, so these are uniform mass density. You can always have objects which have non-uniform mass densities, but let's keep it simple here. And now we want to talk about what is the moment of inertia of all these objects, so that we can analyze if I were to move a or try to rotate a hollow cylinder versus a solid cylinder, which one is easier to rotate if we are doing it about the same axis. So let me list the moment of inertia here. I is equal to, so is it visible? Yes. So this will come out to be, since all the masses are equidistant from the axis, whichever tiny infinitesimal mass you consider, they are all at the same distance from the axis. So they will all add up to be the same amount. So it is the total mass m times the radius of the cylinder. So it's just 1 in front of it. Earlier we got 1 by 3, 1 by 12. It's just 1. What about hollow sphere? So this comes out to be 2 by 3 times the mass m times radius r squared. And again, where do I get this 2 by 3? You have to do this integration over all the tiny masses that's distributed on the axis. When it comes to a sphere, all the masses are not equidistant from the axis, unlike the hollow cylinder, because when you're very close to the North Pole, you're pretty much exactly on the axis itself. So as you go farther and farther from the North Pole, you get farther and farther from the axis. On the equator, you're at the farthest point, and then as you go towards the South Pole, you get closer and closer. So if you average all of those quantities, you get this factor of 2 by 3. And again, you have to do an integration for that, which I won't be testing on. I will be mostly testing on one-dimensional objects, but somewhere else, hopefully, you will be able to learn how to do those averages or integrations over three-dimensional objects. Solid cylinder, this comes out to be exactly half. Again, it's not expected that you might have a very easy intuition to grasp this. Why is it 2 by 3? Yes, you can have a little intuition as to the size of the number, which I will mention in a minute, but to guess exact numbers might be hard. And this is equal to 2 by 5 times m squared. All of them depends on the radius, so that helps us have a hierarchy here: largest moment of inertia, smallest, or smaller, and the smallest. So notice that 1 is, or maybe I should put it the other way, right? So you have 2 by 5 is less than 1 by 2, which is less than 2 by 3, which is less than 1. 2 by 5 is 0.4. This is 0.5, and that's 0.7 to 1 digit, and that's less than 1. So about these axes, and this is very relevant when you're actually rolling all these objects. If you had 4 objects, which was in the shape of a hollow cylinder, solid cylinder, hollow sphere, and a solid sphere, and they all have the same radius, and if you were to roll them, they will all behave differently because they all have different inertia as far as rotation is concerned. And we can easily see that this will resist rotation motion the most, right? Because it has the largest moment of inertia. That means if you were to roll all these 4 objects, this will roll the slowest. And we will try to talk about dynamics in the next class, where this will play an important role. At this point, I will stop. Thank you.
Thank you as well.
Thank you, Blake. Any questions? If not, let me end the meeting.